And with that, good morning, everybody. Gotta have you. And welcome back to Linear Algebra. Plan for today. We've got a quiz for you on Standard 8 as promised, and then we're going to jump into Standard 9, talking about what does it mean to form linear functions or linear transformations between two abstract vector spaces that are not necessarily Rn. And what mischief can we get into with that? As far as office hours go, I've got my usual office hours today at 11 and at 1, tomorrow at 10 and at 1. Standard 9 problems have not been posted. Didn't get that done like I was hoping to yesterday, but that will be up later today or tomorrow. We're going to have an exam next Wednesday. Standards 1 through 9. So just like first exam, you can bring in one sheet of notes front and back with you into the exam. For the exam, probably next Monday. Well, I'll update it today. I'll update Canvas later today because I need to do that for my Calc 1 students anyways. But I'll also update Canvas so you know exactly how many masteries you have going into the exam. And just keep that in mind. Any questions or comments before we get started for today? Anybody here watch Rick and Morty? Anybody remember that episode where, gosh, it was like a few seasons ago where Rick broke into the galactic government and changed the value of the galactic currency so that $1 is worth 0 of itself, and that caused the entire government to collapse. Here's how you can do that. We're going to take $1. What's $1 equal to? Well, $1 is the same as 100 cents. And we all know that 100 is equal to 10 squared. What is 10 cents compared to $1? Well, we know that 10 cents is the same as a tenth of $1. What do you get when you take 0.1 and you square it? You get 0.01. Parentheses. And what is 100th of $1? That is equal to 1 cent, which tells us that $1 is equal to 1 cent. Which, subtracting 1 cent from both sides tells us that $0.99 is equal to $0 or cents, however you want to refer to it, which is going to tell us that $1 is equal to $0, and that is how you topple the government. I think that's applause for toppling. I don't know if you like the government or not.
I think we should go write this on a board in the economics classrooms.
Yes.
See what they have to say about that? Please, someone do that and let me know how it goes. I would be very curious. All right, everyone all right with that?
Well, I'm not okay with that.
Why aren't you okay with that?
It's the switching from the 10 cent to the 0.1 of $1. I don't like that.
What's wrong here? Is 10 cents not a tenth of $1?
It is, but we don't have 10 cents, we have 10 squared cents.
Oh my goodness! Kevin?
The beginning, you didn't put multipliers for them, so you're saying 1 is equal to 100, so the beginning statement's already false, because you didn't specify the cent is times 10 to the -2.
Well, let's start with the assumption that 1 cent is equal to 100th of $1. That's at least true in current economy. And I think the issue isn't actually going from this step to this step. This is actually fine. The issue is here and here. Because if we take 10 cents and we square it, take 10 cents times 10 cents, we're going to get 100 cents squared, or squared cents. And similarly, if we were to take $0.1 times $0.1, we get 0.01 square dollars. How do you make what's a square dollar, you might ask? Well, take a dollar bill, Get your scissors out, cut it perfectly, boom, you're left with the square.
I don't know, facing federal property.
So the moral of the story is, be careful with your units. Because if you're not careful with your units, you can cripple the economy very easily. And with that, it is quiz time. Evens. You all know the drill. Have fun. I'll be back in just a second. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. All right, so here's the scoop. So in Standard 9, we're going to be focusing on how do you find linear functions between two vector spaces. Last standard, we kind of talked about what vector spaces are, how do you find subspaces of them, how do you find a basis for a subspace, how do you find the dimension for a subspace, which are all things that we've kind of talked about in previous standards and working over Rn. The other thing we did in Rn a lot that we haven't talked about yet is looking at linear transformations. Like, what does it mean to have a linear transformation from Rn to Rm? How do you find the image? How do you find the kernel? How do you find the rank, the nullity, etc., etc.? And we have a little bit of a conundrum here. Because if you think about it, all of our linear transformations from Rn to Rm we defined in terms of matrix multiplication. We said, oh, if you want to go from Rm to Rn, you take a vector in Rm, you multiply by a matrix of the appropriate dimension, and you get a vector in Rn. And that's what a linear transformation was defined to be. It's a little bit harder to do with an abstract vector space, though. Because what does it mean to multiply a polynomial by a matrix? Or to multiply a function by a matrix? Doesn't really make too much sense. So, anybody recall, what did we say in Standard 3 was another way to think about linear functions? So if you recall, we had a theorem back in the day that said a function is linear from Rm to Rn if and only if it satisfied a couple nice properties. One was that it broke up nicely over addition, meaning you had a property that T of V plus W was equal to T of V plus T of W. And the other was that it kind of behaved nicely that you could pull scalar multiples outside of your function. Meaning that if you take T of R times V, you got R times T of V. And we said back in Standard 3 that a function that satisfies these two conditions from Rm to Rn has to be linear. And vice versa. If we have a linear function from Rm to Rn, then it has to satisfy these two properties. So what we're going to do in talking about how do you take, what does it mean to take a linear transformation between two abstract vector spaces? It doesn't really make sense to define that in terms of matrix multiplication. Because unless your vector spaces are Rn, copies of Rn, what does it mean to multiply by a matrix? So instead, this time around, we're going to take these two properties as our definition of what it means for a function between vector spaces to be linear. And that is going to get us into some mischief. All right, 1, 2, 3. 1, 2, 3. 1, 2, 3. So here's the scoop. We're going to define a linear function between vector spaces to be a function that satisfies essentially those two properties. So we're going to say, given vector spaces V and W, a linear transformation, or a linear map, however you want to call it, is just going to be a function f that goes from V to W. It's going to take in elements of V as inputs and spit out elements of W as outputs, such that for all vectors and all scalars, you want f of V1 plus V2 to always be equal to f of V1 plus f of V2. And the second condition we want is that f of scalar times anything in V, we want to be the same as scalar times whatever f of V is equal to. In the case of Rn, we said way back in standard 3 that these two conditions were equivalent to saying a function from Rm to Rn is linear. So now we're just going to take this to be our definition, because our matrix multiplication definition of linear function doesn't work, but this still does. This is still something we can talk about for between any two vector spaces, assuming we have ideas of addition in the two vector spaces, and we have some idea of what scalar multiplication looks like in the two vector spaces. So let's look at an example. I want to take a function f that goes from linear polynomials, so polynomials of degree less than or equal to 1, and it's going to spit out vectors in R2. And the way it's going to work is we're going to have a function that takes in a linear polynomial, a polynomial of degree less than or equal to 1, f of ax plus b. We're going to say is going to be the vector AB in R2. So unlike the previous functions we've looked at in past standards where we take in vectors in Rm, spit out vectors in some other Rn, this is going to be an example of a function that takes in polynomials and spits out vectors as outputs. So our inputs and outputs are two very different types of mathematical objects. Polynomials versus your standard R2 vectors. It's going to turn out, though, this is still going to be a linear transformation, meaning it's going to have some nice properties to it. So what I want to go, so for instance, if we were to take in f of 3x plus 6, we would get the vector 3, 6. If we wanted to take f of negative pi x plus 17, we would get negative pi 17 as our output. So it kind of gives us a nice way to transform a polynomial into a corresponding vector by just sort of peeling off the coefficients of the polynomial. So what I want to do is I want to check to see that this is a linear function. Spoiler alert, it is. But, okay, good, I'm still recording. But in order to check that, we need to check each of these two conditions. Abby, which one do you want to check first? Let's check our first condition. So the first condition tells us if we add two elements in our first space, in our domain, and then plug in the function, we should get back the same thing as if we took f of first element plus f of second element and add them together in our second vector space, in our codomain. So let's try taking two arbitrary elements of the linear polynomials. So I'm going to say if ax plus b and let's say cx plus d are both elements in our domain, and I'm using variables here so that these could represent any elements in p less than or equal to 1. They're arbitrary. I'm not plugging in specific ones. What we would get is f of the sum ax plus b plus cx plus d And we need to see what we would get if we wanted to evaluate this. Hopefully the same thing as f of ax plus b plus f of cx plus d. So, how would I evaluate this? Liam?
You add up the parts with the x and multiply by x and add up the parts without that.
Okay, so you want to kind of combine the x terms and the constant terms of the polynomials?
Yeah.
Sounds good. See, if we did that, we get a plus c times x plus the constant term b plus d. And then we need to plug that into our function. So actually, what vector in R2 would this spit out if we tried to plug this in to our function up there?
It would be a plus c and then b plus d.
B plus d, like that? Oh, let me close it, like that?
Yeah.
Yeah, I like it. You take the coefficient in front of your x term, which is a plus c. That's the first coordinate of the output vector. You take your constant coefficient, and that's going to be the second coordinate of your output vector. And wouldn't you know it, I think we can write this as the sum of two vectors in R2. Riley, how can we break this up nicely?
You could do, sorry, a plus b and then c plus d.
Well, keep in mind, these both need to be two-dimensional vectors if we want to write it as addition of things in R2. So when you say a plus b and c plus d, those are both scalars, right?
Yeah, like a on the top and b on the bottom.
Ah, so like the vector AB plus the vector CD? Yeah, we could definitely do that. What do we know about AB? Well, that's going to be f of ax plus b. What do we know about CD? Well, that's f of cx plus d. And what we've shown is that the first condition for linearity is satisfied by this function. With the idea being, if we add two polynomials and then plug it into the function, we're going to get the same result as if we plugged in our two polynomials originally into the function and then added the corresponding outputs in R2. So in other words, adding in polynomial land and then plugging in the function is the same as plugging in the function twice and then adding in R2. So that there's this nice sort of correspondence between how does addition work in your first vector space, because this is addition that takes place inside of V, whereas this addition takes place inside of W, but if you plug in and then add, or add and then plug in, you get the same result either way. So, got condition number 1 satisfied. Any questions or comments about that one? Ashley, you look amused.
I'm just laughing because earlier before you started class with the example of the $1 and 100 cents and like all the adding into that.
Oh, you're still thinking about
I'm
that?
like, I don't know. Like this makes sense, but it's just in the back of my mind. Like, what if something's slightly off? And we have them. Yeah,
Then we have bad news bears is what happens.
I know it's not, but it was just.
A what if scenario?
Yeah.
Fair enough. So let's check our second condition. So the second condition tells us if we take any vector and we do scalar multiplication in V and then plug in our function, that should give us the same thing as if we plugged in our function first for V and then did scalar multiplication by R in W. So this is scalar multiplication inside of V, this is scalar multiplication inside of W. And so just like how for a linear function, if you do addition in one and then plug in your function, or plug it in first and then do addition, it comes out to the same thing. Condition 2 is saying the same thing should happen with regards to scalar multiplication. So let's test this out. So we're going to take again an arbitrary vector in V. So if ax plus b is an arbitrary input vector. And Cameron, I need a name for a scalar, like R or S or something. K. Ooh. K for Cameron or K for Kevin?
Oh.
And let's say if K is a scalar, I like it either way. We need to show that f of r times our vector ax plus b, we want to show that that should come out to the same thing as r times f of ax plus b. So in this case, we're going to do our scalar multiplication first. So if I were to take ax plus b and multiply that by the scalar r, Paul Joshua, what would that give us? It would give us, well, f of what expression?
RAX plus RB.
Yeah, the scalar kind of gets distributed to both the ax term and the b term, so we would have f of ra times x plus r times b. If we plug that then into our function f that takes in polynomial and spits out a corresponding vector in R2, what would get spat out here if we plugged in RA times x plus RB?
Vector RA, RB.
RA, RB. I don't think in Arby's. Also, I like how apparently Cameron, I asked you for a K and then I just went right back to R because that's what I did in my notes. Sorry, Cameron. Apparently your choice didn't matter.
It's okay.
What happens if we pull a scalar multiple of R out of this? What's going to be left in our vector? R. AB? Yeah. And what is AB? Well, we know that AB is equal to R times, well, we know R times AB is equal to R times F of AX plus B. And our second condition checks out. Because if we do our scalar multiplication in polynomial land first and then plug in the function to get RA, RB, we get the same thing as if we plugged in AX plus B into the function first and then did scalar multiplication in R2. The order in which we plug in our function and do scalar multiplication doesn't matter, in other words. Similar to how over here, if we did addition in polynomial land and then plugged in our function, gave us the same thing as if we plugged in our function to both terms first and then did addition in R2. And the fact that both of these conditions are satisfied is going to tell us f here is in fact a linear function. F is a linear function since conditions 1 and 2 are satisfied. Any questions or comments about this?
So is this f a subspace?
F is a function. F is not a subspace. A subspace is a set of vectors. F is just a single. It's a function that takes in vectors from your first space and spits out vectors in your second space. So when we talk about subspaces, we usually think of things like a set of vectors in p less than or equal to 1, or a set of vectors in R2, not a function that necessarily goes between them, which is just a way of going from one vector space to another one. However, if you're eager to find subspaces, then turns out, just like with linear functions back in standard 5, we can always find two subspaces that get associated with this sort of linear function, that being the image and the kernel. So let's write that down. So back in standards 5 and 6, we did a lot of, hey, here's a function from Rm to Rn. Let's find the image, let's find the kernel. And then it turns out those are always subspaces. gonna turn out, as long as you have a linear transformation from Rm to Rn, the image and the kernel will form a subspace of the corresponding vector spaces. It's going to turn out to be the case that if you have a linear transformation from one vector space V to another vector space W, so if this is a linear transformation, a linear function, then we can define the image of F is going to be the set. Image of F is the set of all elements in your codomain W, such that little w is equal to f of some little v, for some little v element of big V. And it's going to turn out to be the case that you can define the kernel of F similarly, where the kernel of F is going to be the set curve of F is the set of all elements little v and big V such that f of little v is equal to 0. So in other words, we can define image and kernel of a linear map between two vector spaces in the same way that we could define it between Rn and Rn. The image is just is the range, the set of all things that actually get mapped to by your function. The kernel is a set of all things that get mapped to 0. Yeah, Henry?
Yeah. Just a quick question. In our notes, it says for the kernel t of v equals 0. Does that mean anything?
It does mean something. It means I have a typo in my notes.
Okay.
It should say f of v equals 0.
Okay.
Originally, I wrote this where t was the name of the function from v to w. And I'd say, let's change it to f. And apparently I forgot to change that t back to an f.
Okay.
In the book it calls it t, I like calling it f better, because f makes you think of usual functions you like working with. I got a question. What's that? What do we mean by 0? Because keep in mind, 0 does not necessarily mean 0
Is it the 0 element?
of,
V. No, W.
it is one of those.
W.
It is. So 0 here is a shorthand for the 0 element of whatever your vector space W is. So if you remember, back in the last standard we said that every vector space had to have a 0 element, meaning something that if you do addition by that element in that vector space, nothing changes. Depending on what your vector space W is, 0 could mean something like the 0 vector, 0, 0, in the case of R2. It could mean like the 0 polynomial. It could mean the 0 function, where f of x is always 0, if we're looking at, say, the set of all functions from R to R. 0 here is sort of a shorthand for saying the 0 element of your codomain. And so what we're defining the kernel to be of a function is the set of all elements in the domain that map to the 0 element in W. So let's take a look-see. What's going to be the image of this linear transformation? It takes in a vector or it takes in a polynomial and spits out the vector AB. So the image is going to be, by definition, all elements V in R2 such that V is equal to f of, or let's say W in R2, such that W is equal to f of V for some element V that's a polynomial of degree less than or equal to 1. So here's a question. What polynomial, or what vectors in R2 are going to get mapped to by some polynomial in p less than or equal to 1? Maybe I should ask a different question. Are there any vectors in R2 that are not going to get mapped to by some polynomial? Liam?
No.
Henry?
I would say no.
I would agree. I thought this one's going to be all of R2. Because every vector in R2 is going to get mapped to by some polynomial. You give me a vector in R2, any AB, well, I can give you a polynomial that'll map to it. Just take the corresponding AX plus B. Every vector in R2 gets mapped to by some polynomial. How about the kernel of F? Well, by definition, that's going to be the set of all vectors V, or all polynomials of degree less than or equal to 1, elements in your first vector space, in the domain of your function, such that f of V is equal to 0. Well, what is 0? It's the 0 element of R2 here. So that's going to be all polynomials in p less than or equal to 1 that map to the 0 vector 0, 0, which is the 0 element of R2. So what polynomials under this function are going to map to the 0 vector 0, 0? Elmar?
0.
The 0 polynomial?
Yeah.
Anything else? Nope. Turns out this one's going to have a trivial kernel. Because it turns out that the only polynomial that'll map to 0, 0 is going to be the polynomial 0x plus 0. And so that's how we can find the image and the kernel of a linear transformation. Conceptually, it's the exact same as it was for functions from Rm to Rn. Kernel is the things that get mapped to the 0 vector. Image is a set of all things that get mapped to. The only difference here is that with our image in our kernel, this time the image in the kernel could be made up of elements from some abstract vector space rather than necessarily being vectors in Rn or vectors in Rn. Yeah, Liam?
If you had a function that had ax squared plus bx plus c, and you defined it as being bc, so it always goes to the thing bc, except if the a is not equal to 0, then it would be going. Oh wait. Never mind. No,
I highly suspect that what you were about to suggest is not a linear function.
Yeah. Because
You could consider this a linear function. Take in a degree 2 or less polynomial, spit out BC. In that case, we would still say that the image is all of R2. I think the kernel of this would be the set of all vector, or the set of all polynomials ax squared plus bx plus c, where b and c are equal to 0. But not necessarily, but it wouldn't be trivial because you could still have like x squared be in the kernel, or 2x squared, or 5x squared, or negative pi x squared. So that would have a non-trivial kernel, but it'd still be a linear map. All right, that's gonna do it for today. When we come back Friday, we're gonna talk more about kernel and image of linear transformations. We're gonna talk about how do you find the rank and the nullity of a linear transformation. Spoiler alert, it's exactly the same, defined exactly the same way that it is for a couple standards ago. And then we're going to start having some fun talking about isomorphisms of vector spaces. What does it mean for two vector spaces to be mathematically the same, in big air quotes? Have a good one, everybody. See y'all on Friday.